progressing forward with homework 8 material today. Meanwhile, hopefully you're finishing up homework 7 and starting to turn your attention to studying for the exam. That won't be until a week from today, I think, right? So what I'm hoping is that by Tuesday, I will have finished enough of homework number 8 material to set you loose on that in a significant way when you're obviously ready to do that after the exam. And also be able to set you on the path to starting homework 9 concurrently or shortly after as well. So the hope is that when our next lecture after the exam hits, we might already be on homework 10 material or close to it. Okay, any quick questions before we get started? Yeah.
Sorry, just between incoming pole, is that far?
Here?
Yes.
Incoming polarization and transmission axis. Administrative or logistical question? Yeah.
You're gonna give us video or something?
Correct.
Okay.
Yes. So basically I'm gonna kind of walk you through the various cases. It's a lot easier for me to do on a computer because I can do all scale drawings and without having you watching me painstakingly try to fumble through them in class in real time. So it's just a topic that lends itself pretty well to it. Okay, so let's review. We have this thing called a polarizer. This is a man-made manufactured material. It has a preferred axis called the transmission axis, TA for short, and that is the preferential axis along which linear polarization is allowed. So if you send in polarization which is exactly lined up with the transmission axis, 100% will go through for an ideal polarizer. So it goes through exactly how it came in. If you send in something which is exactly perpendicular, the incoming polarization is perpendicular to the transmission axis, none of it will get through. It will be blocked. And of course, every other polarization which is diagonal relative to the transmission axis can be thought of as a composite of a component that gets through and a component that does not. So here, what we find going through, these are all going through the polarizer, is that what comes out is not quite as large as what it came in, but it's not blocked entirely either. And notice that the polarization is going to be lined up with the transmission axis that it just went through because that's the only component that survived. So our equation, as I showed you last time, it's literally just throwing away one component and keeping the other. So the electric field amplitude on the way out will be what goes in times cosine of theta. And theta is measured between the incoming polarization and the transmission axis. Also, corollary to remember here is that the outgoing polarization is parallel to the transmission axis because that's the only component that survived. So remember that it's not just that the amplitude is reduced, it's just that it's the polarization also, in a certain sense, looks rotated from the way it came in. Now there's only one thing to stop us from finishing up the final polarizer equation that we need to have, and that is a brief revisit to Physics 1 to talk about waves. Of course, we talked about sound in Physics 1, and let's compare it versus light now. They're both waves. So all the stuff we learned about waves, we can bring right over here. For instance, we can bring over V equals F lambda. Hopefully remember that. That's the relationship between the wave speed, frequency, and wavelength. We have a wave. It has a speed. It has a wavelength. And at a given fixed observation point, you can talk about the frequency at which the wavelengths pass, or the period, which is the time it takes for one to pass. And again, frequency is 1 over period, so on and so forth. So hopefully these are all the very, very basic wave things from Physics 1. And also, as far as sound goes, there are two quantities that we generally like to talk about, pitch and loudness. So these were the essential two quantities carried by a single sound wave. Is it a high note or a low note? Bass or treble? And how loud is it? Everything else we talked about were kind of more kind of how you tell a flute from a clarinet. That's a higher level thing called timbre, but these are the two essential properties of a sound wave: pitch and loudness. Does anyone remember what quantity pitch was corresponding to? You hear a high note or a low note? Frequency, exactly. So frequency is pitch. A musical note has a certain frequency. It's measured in hertz. Does anyone remember what property of a wave was associated with its loudness? Intensity is the actual direct measurement. That's measured in watts per square meter. This over here is measured in hertz. So intensity was watts per meter squared. It's basically energy per time delivered per area. Okay. Now, I do want to remind you that intensity was proportional to the square of the amplitude. The amplitude for a sound wave, by the way, just to remind you, we had two different pictures for the amplitude. One was called the displacement amplitude, one was called the pressure amplitude. Okay? But the point being is that if you double either one, it will be 4 times the intensity. Okay? So that's exactly the same thing we do with light waves now. For frequency, instead of pitch, it's color. All right? So for visible light, we have, for instance, Roy G. Biv. That is a listing of the visible light from lowest to highest frequency. So this is increasing frequency going from R to V. Red is on the order of 430 terahertz. It's a very high frequency. And then violet's 750 or so. That is the frequency range of visible light. You can, of course, use V equals F lambda. We learned that the speed of light in a vacuum, we reserve 3 times 10 to the 8th meters per second. We reserve the letter C for that. So you can also calculate the wavelengths, which these correspond to. Of course, we know that if you increase your frequency, you're going to decrease your wavelength. So since I've already listed them in order of increasing frequency, I also have listed them in order of decreasing wavelength. This is about 700 nanometers. It's about 400. As we'll talk about, frequency is a better measure, but it is also handy to mention wavelength. Of course, there are other frequencies of light that we cannot perceive with the naked eye, but these are the visible range of frequencies, which we call color. Okay? So, the reason I'm introducing this chart is really for this fourth and bottom thing. The corresponding quantity for loudness is brightness for light. So we commonly mix up the senses. We kind of play it fast and loose. You might say, wow, that's a loud shirt, right? What you mean is it's a very bright, weird looking shirt, right? Okay. So, or you can say, like, you know, that instrument sounds very bright, okay, or something like that. Or you could say, I guess you could say that, like, music is like color for your ears, or something like that. I don't know. You can see all this stuff. So the point I want to make here is that, again, the intensity which is the brightness that we actually measure, is not actually directly related to the amplitude, it's related to the amplitude squared. So that's the final little touch we need to put onto our equation, because we don't really measure E, we measure a quantity proportional to the square of E. So we convert this into an equation which relates directly to the intensity, which is the property we'll observe with the naked eye. So of course, if the amplitude is reduced by cosine, then the intensity will be reduced by cosine squared. This right here is called the law of Malus. It's the equation for an ideal polarizer. It's very difficult for a real-world polarizer to exactly follow this equation, but highly well-manufactured polarizers do a pretty good job. So this equation you can find on your equation sheet. We're going to try to take it out for a spin here in a moment. But I do want you to remember not just the equation, but remember a couple important things. Remember, first of all, how the angle is measured. That's number one thing that can go wrong is you identify the angle incorrectly. It has to be that angle. Another thing that is not just sitting there looking at you in the equation is remember that the outgoing polarization is parallel to the transmission axis. And then the final thing I need to show you is what does a polarizer do to unpolarized light? So let's say I have unpolarized light and I shoot it into a polarizer. Well, this is going to be tricky because there's no clear theta to use on the incoming side. Of course, every theta is present. So the range of angles that this incoming light will experience with the transmission axis, well, some stuff in the unpolarized light is perfectly lined up. Some stuff is perfectly going to be blocked. And so some averaging will have to be involved. And as you can probably imagine, the average angle is 45. So there's as much stuff that's closer to 0 that's going to be more allowed through as there is stuff closer to 90 that's going to be more blocked. The average angle that all of these different polarizations in the unpolarized light are going to make with the transmission axis is 45. So if we plug that into the equation, I out equals I in cosine squared of 45. Well, cosine squared of 45 is just a half. So what that means is that if you send in unpolarized light into a polarizer, it's going to cut the intensity exactly in half. Now, that's what the equation tells us, but remember that if this is the incoming intensity, the outgoing intensity is not only half, but it is now linearly polarized parallel to the transmission axis it just went through. Those are the only components that survived. Okay? So if you take a look at a polarizer like this, the reason it looks kind of shaded, right, is because if you have unpolarized light, like from this light fixture going through it, the intensity gets cut by a half. Okay? Does that make sense? Okay, so let's start playing around with multiple polaroids, or polarizers. So let's say I have unpolarized light. I send it through this, and then I send it through this. So what will happen? Let's say I have an initial intensity I naught. When I go through here, it's going to become linearly polarized, parallel to the transmission axis it just went through. Its intensity is going to be cut by half. And what is the next polarizer going to do? Not going to affect it whatsoever. Whatever got through the first one is just going to go right through the second one. So that is a complete pass-through. Okay? So let's try that one out. So if I have one polarizer like this and I put a second one, not a substantial difference. You may notice a slight dimming, but that's because of non-ideal polarizer behavior, right? So once you've polarized it, if you put a second one with the transmission axis in the same place, not much difference, okay? You can see here I have a region where both of them overlap and then them by themselves, and you notice there's not a whole big difference, right? So let's try another one. Start with the same thing, unpolarized light. This one we know is going to cut the intensity in half. And now let's put the second transmission axis like this. So how much is going to get through? 0. So it's 100% blocked. We linearly polarize the light to the first polarizer, and then we put the second transmission axis such that it's blocked. So let's try that one out. Okay? So I'll take the two transmission axes and I'll rotate them 90 degrees. You can see it goes black, right? So there's nothing getting through. See that? Okay. So, by the way, liquid crystal displays work like this, LCDs. So basically what you have is you have a liquid crystal, and depending on how you apply the electric potential, vertically or horizontally, if you have two layers and you line them up the same way, you get this. But if you apply a 90-degree electric field, you get this. This could be like the one in a digital display, right? Because that particular cell, the transmission axes are 90 degrees. So that brings up an interesting point, is that whether or not you're part of the one on the digital display, or you're over here, where it's still just one polarizer, or two polarizers that are lined up the same, like one of these guys, it's still polarized coming out. So all of the light from this display is polarized. So obviously the parts that are black, those are cells where the transmission axes have been put 90 degrees. But the parts where you can see, they are still polarized. It's just that it's going through two layers where the transmission axes are the same. So this highly suggests that if we went up to this, we'd be able to see the polarization. So you can see, for instance, that the display is fine like this. That's because I've lined up the transmission axis to let the light get out, but then I can twist it, and I should be able to make it go black, right? Now, this is fun if you're wearing polarized sunglasses, like I said, the gas pump. Okay, you can have lots of fun with this. You can go like this and make the display turn black. Okay. There are also some cars where the heads-up, all the radio and everything like that are also LCDs. They have to be really careful how they design those things so that if you're driving with your sunglasses on, everything is totally black. Okay, including the speedometer and everything. Okay. We'll get to all that stuff in polarization in the real world in just a second. But before I move off this topic, I want to just give you a very nuts and boltsy example where we go through the calculation. Here it was easy to do by inspection, and that's always a good tool. But it, of course, was relying on the fact that we were either 100% blocked or 0% blocked, but not somewhere in between. So let's just go ahead and do a real simple example. I'll show you some of the common things that people get wrong. I'm going to have one transmission axis like this. And I'm going to have the next one like this. It's tilted, and so of course I have to give an angle that it's tilted by if you're going to have hope of doing this quantitatively. And then let me put the next one like this. So I have 3 different polarizers. Actually, do I want to do that? Let's not do that. Let's have the last one be horizontal. I'm not sure I have the numbers written down for this, but I think it's more interesting, and it leads me to a more interesting point. So let's send an unpolarized light, I0. We send it through the polarizer. It cuts the intensity by 2, and it also makes it linearly polarized. By the way, I'm going to post an applet for you, which on homework number 8, where it can literally do this all for you. You can choose whether you want to send in unpolarized or linearly polarized light. You can have two different polarizers afterwards. You can rotate their transmission axes however you want, and it'll show you the path of the light through. So we have this going through here, then it arrives over here. Let me draw it next to there. So what angle should I use in my calculation for this? 30 degrees, yeah. Because the angle between the incoming polarization and the transmission axis is 30 degrees, so the intensity will be reduced further. So whatever went in, we have to multiply by cosine squared of 30. Remember that what escapes is going to be reduced in intensity, but also parallel to the transmission axis it just went through. Okay? This one is supposed to look like it's 90 degrees from the vertical. But be careful. That is a very common way for a series of polarizers to give all of their angles from the vertical, just as a common reference. But in this next calculation, we do not want to put in 90 degrees. What angle do we want to put in? 60 degrees, that's right. Because it came in, tilted 30 degrees to the vertical, now it's going to make 60-degree angle to the horizontal. So whatever went in, which is I naught over 2 cosine squared of 30, we now add additional factor of cosine squared of 60. So whatever this factor is, someone cares to tell me what it is, I can put it up there. Otherwise, it's just some number. So cosine squared of 30 times cosine squared of 60 over 2. That is some number. And that number times I naught, this is the factor by which it's reduced, right? You can express it as a decimal or multiply that number by 100 and get it as a percentage, right? It's clearly going to be less than originally because at every stage it's getting cut. Its intensity is being cut. And not to be remiss, I also want to point out that what goes out is going to be horizontally polarized light because the very last thing it went through was a horizontal transmission axis. Okay? So be really careful there. Don't just plug in 30 and 90. You should be plugging in 30 and 60. Are there any questions on that? Does anyone have the number handy? It doesn't matter. It's a number, okay? So the other thing that the reason why I switched it from the original one I had the number handy, but the reason I switched it is because if you look at something, it's interesting, you have the first and last polarizer, it seems like they're mutually exclusive. The first one and last one, it looks like this. So you may be surprised that anything is able to make it out, because if it made it through this one, it's vertically polarized, but in order to make it through the last one, it has to be horizontally polarized. Well, the middle one actually facilitated the escape, because the middle one, while it does cut a component off this one, it also rotates the polarization such that the last one has something to do. So let me try to show you this. So here I have two polarizers where their transmission axes are mutually perpendicular. That's this one right here. But I'm going to put in another one at a diagonal, and you should be able to see that you can now see through it. Can you see through it a little bit? Now notice at the corners here, where it's just the first and last one, it's still completely black, right? But through the middle polarizer, yes, it cuts the intensity further, but it rotates the polarization so that the last one still has something to pass. So if you want to, we can try it here. If we were to take the diagonal one and align its transmission axis with either one of the other ones, well then of course there's nothing left. That everything gets cut by the other one, right? But if the middle one is diagonal, then you will get something through. Because the middle one accomplishes rotating the polarization such that the next one has something to grab onto. All right? So, I guess I can tell you a little bit about, for instance, 3D movies. You guys know about stereoscopic vision, right? Why you see in 3D, you have two eyes from slightly different vantage point. You know that's how you get depth perception? Possibly? Okay, yeah, so of course the challenge in a movie is you're projecting onto a screen. If you could project two different pictures that are slightly offset, same distance as your eyes, you could get the illusion of depth. Now, the very original 3D movies, they literally put a red and a green picture slightly offset, and then you had a red and a green lens, and you could see 3D movies. Problem, of course, is that everything has to be red and green, and that's really not very exciting. So the next level is full color, but use polarization. So what they can do is project two images where one is sending you horizontally polarized light and one is sending you vertically polarized light. So then you look like this. Okay? So that allows you to send two pictures, and each is sure to get to each eye. Now, one of the interesting things about that is that if you tilt your head slightly, then you start to get mixing of the two channels. So people would report getting headaches and stuff